Hi class, it's Bill Berry back with the last video I believe for this first half of the week regarding complexity notation and recursive sort methods. So far we've talked about complexity notation and we looked at merge sort, which is the first of our two recursive sort methods that we're going to look into, but we still have some more fun to have, so let us jump down to recursive sort methods. We've already been through these slides, so I'll just remind us that we talked about the merge sort, we looked at its complexity, we did a demo, and now we're going to talk about the quicksort. So how's the quicksort different? Well, again, let's talk about an analogy that I think is interesting for this. First thing to notice is that I think the two recursive sort methods actually have better analogies for real life. You could look at a bubble sort, but when you look at that, you think, why would I ever use that? Like in real life, how would I ever think to do a bubble sort? But these two, I think, really have what seems like a real life implementation, right? A real life analogy. So the stack of graded papers that were already sorted that I needed to merge is a really good example for merge the merge step in a merge sort. And with quicksort, I have a great analogy here too. Let's say that we have an earthquake in Seattle, not unknown, and let's say CDs fall off the rack. And yes, we have CDs. So if CDs fall off the rack and they're in a big pile on the floor and they get jumbled, of course I will feel compelled to get them back into the alphabetized order that they were before they came off the shelf. But what I'm not going to do here is do a bubble sort or an insertion sort because that would just seem ridiculous and very time consuming. It just doesn't even sound right, does it? But one thing that I really would do, in fact, one thing that I really do is if I have a bunch of CDs that are out of order, the first thing I do is do a very loose sorting where I just take everything that comes early in the alphabet and push it into one pile, and everything that comes later in the alphabet and push it to a different pile. That way, I've done this rough sort, and now I can go to that first pile and do the same thing, but now I pick a middle that's sort of, a fourth of the way through the alphabet. And again, I take that pile and turn it into two piles, one that's earlier and one that's later. And I can keep doing that until I get down to where individual letters are together. All the A's are together, all the B's, and that's as far as I'm sorting, right? Maybe I could go all the way down, but as long as I have all the A's together, I'm kind of happy. So this is a real thing that a person does, and that's what a quicksort does, exactly that. What you need to do is pick a pivot point. The pivot point says, how are you going to decide what's halfway? Now with the alphabet it's easy because I just say, well, I can either count 13 letters in, or just because I kind of know how these things go, maybe I say, well, I'm going to go everything through M, right? Either pick a letter, pick something that makes some sense. So you've got to pick a pivot to say, hey, I'm going to divide it, but based on what? And then you're going to make sure that everything that's smaller than the pivot goes to one side, everything that's not goes on the other side. And recursively, I'm going to continue that until it's all the way done. Notice this doesn't have the two-step of the breakdown and the merging that the other algorithm does. And in fact, notice that it does in-place sorting. So you don't need the extra space that you do for the merging, because when you're picking up those numbers and picking the largest or the smallest one, you've got to pick them up, right? You've got to actually put them in a separate little tray. But that does not happen here. The quicksort can work just fine. Now, the algorithm that I'm going to show you when we look at code, we're going to use a right element pivot. If the things are in random order, you don't really know anything about the range of the data, then you really can't pick a smart pivot, and you can just pick one either at random, which algorithms don't tend to do, or you pick one, in this case we'll pick one to the right. So it doesn't really matter. Pick a pivot and then move everything. So the general thing I want to tell you is, because of its efficiency, even though on paper it doesn't look quite right, it does outperform the merge sort in the general case. This is the go-to sorting method that if you just needed to pick one and you didn't know anything about your data, you'd probably pick this one. Now it does devolve in certain cases. It does have a bad case if everything is already sorted, or if it's reverse sorted. This is painful, because all of the pivots are going to be bad choices. We're going to see that in a minute. But in the general case, it's pretty darn good, right? N log n, just like the others, but space, it's only going to use a little bit of space. It's not going to use all this extra space like the merge sort. So log n amount of space, not not the other. Okay, so let us do now a quick demo. Again, I'm going to fall out of PowerPoint presentation mode so that we can actually look at these things ourselves. So here we go. Okay, so I think that'll work. Now, what we're going to do here, completely different approach. What we're going to do here is that we're going to have one little pointer that we're going to think of as the partition, has a P on it. And then we're going to have another little pointer that we're going to think of as the wall. The wall is going to represent the dividing point between the items that are less than the pivot and the items that are more than the pivot. So the wall is an important point. Now we're also going to have another index that's going to march along and look at item by item. I'm not having a separate pointer for that. We'll just sort of remember and we'll go look at those items. But when you're writing the code, obviously you're going to have something that has to go marching along there. First thing we're going to do, we have to pick a pivot. For this algorithm that I'm going to show you, we're going to pick the last element as the pivot. Why? Well, you got to pick something, and if the numbers are completely random, you can't really pick any smarter. Again, if we knew the range, maybe we could, if we knew that the numbers would never be outside a certain range, we could be smart, but we don't know that here. So let's just pick the last one. There are other code implementations that do something different, but that's the code I'm going to show you in a minute. The next thing we do is we pick a position for the wall, and we're going to start the wall being over here because this is the dividing line. Just to the right of this thing is the dividing line between the things that are less than the pivot and the things that are more. But we haven't looked at any elements yet. And since we haven't, the wall is going to start at 1 less than this. The wall is going to actually start at -1 in an array terminology. Does that make sense? So we have the dividing line is right here, nothing's to the left of it because we haven't inspected anything yet. So here's how it works. You're going to look at each number in turn. We look at the 5 and we compare it to the pivot and we say, is it bigger than the pivot? If it is, we're going to leave it exactly where it is and we're simply going to move on. All right? We're going to simply move on. So if the number is greater than the pivot, just move on. So now we look at the next number and we say 2. 2, wait a minute, 2 is smaller than that, so that needs to go to the left. So what we're going to do now is we need to take this wall, remember the wall is pointing right here, and we need to swap this number with the thing that's just to the right of the wall. So we've got to swap the 2 and we've got to swap the 5. Okay, to get those in order. And now we're going to advance the wall. So again, we think of it as being here, but there's no such thing as pointing in between array elements. So it's going to be just to the right of this one where the wall lives. Does that make sense? So we've now looked at those two, and everything, again, think of this as being here. Everything to the left of that is smaller than the pivot. Everything to the right that we have inspected so far is to the right of the pivot. Okay, so now let's go forward. We look at 6. 6 is larger than 4. Perfectly fine. Moving on. Look at 9. 9 is larger than 4. That's perfectly fine. Moving along. We get to 3. We say, wow, 3 is smaller than that, so what do we need to do? We need to swap it with the thing to the right of the pivot. So we're going to swap the 3 with the 5, I don't care if I put them exactly right, that's fine, and I move the wall up by 1. What do we do next? Well, we've looked at this one, we looked at the 5, we looked at the, where were we? I don't know. We look at the 5, it's greater, we looked at the 7, it's greater, we looked at the 8, it's greater. Everything is good, right? So we now reach the end. We have gotten to our pivot. We have one more important step. Since this is at the end, what I need to do now is one more swap. Again, to the thing just to the right of the wall, I'm going to swap it with the pivot. Last step, got to swap with the pivot. Now, I'm going to move this out of the way because we're sort of done with this now. What we have now is actually 3 lists. This is sorted. I don't actually need to come back and look at 4 again because 4, being the pivot, is guaranteed to be in place. But what do I have now? I have 2 smaller lists to the left. I need to recurse to the left, and I need to recurse to the right. On the left, I'm going to pick this as the pivot. right? You're going to go through the same operation. You're going to say 2 is less than. You're going to go through this whole thing. You'll end up with a list that looks like this. You'll recurse to the left. When the list is one element, that's just returned, so we know that that's sorted. So recursively, it's going to get all of those in place, and then you're going to recurse to the right of the 4. So the 9 through the 6 have to be sorted, all right? So let me move those over a little bit just so we can see them. Okay. Again, you're going to pick a pivot. So here we're going to pick the pivot here. You're going to set the wall to here. You're going to see, is this larger? Yes, do nothing. Is this larger? Nope, it's smaller. I need to swap it with the thing to the right of the wall. So I'm going to swap the 5 and the 9, and I'm going to move the wall over. 7 is greater, it's fine. 8 is greater, it's fine. I've reached the pivot. One final step is always to swap the thing just to the right of the wall with the pivot item so that we get that in place. And now we know that this is sorted. I recurse to the left. It's one item. That's done. Now I recurse to the right. You see what we're going to do? We're going to keep going through and do this exact same thing all the way down. 9's the pivot, 7's smaller, swap it with the thing to the right of the wall, move the wall over. 8 is smaller, swap it with the thing, move the wall over. We've reached 9, swap it with right here, which is itself. 9 is now sorted, recurse to the left. You see how this is going to go, right? So recursively, you go all the way down, recursing through the first list, then going left, then going right, and then you keep going recursively all the way through and follow the same method. And again, you're going to eventually get to 1s, and then 1s and 2s are going to sort of figure themselves out. You're going to get that sorted. You're going to get that sorted. Now the whole list is sorted. Whew. So that's how the quick sort works. Okay, let me put us back into presentation mode. Okay. So let me grab my pen in case I need it, or laser pointer. Okay, so let's go back here. So this is trying to describe the algorithm. Hopefully that all makes sense. This code picked up the right code element. We'll look at that in a second. And it does in-place sorting, right? So the one that you want to try is the really bad case, which is if it's all sorted, you're going to see you're going to pick a pivot and then do a whole bunch of swapping of elements with themselves. All right, so you're gonna have a whole bunch of really devolved bad scenarios. So try that if you want to see that the algorithm does a whole bunch of comparing and then doesn't do much work along the way. And notice for each recursive call, you're going to need a little bit of space, but it's not really much space. So log n is pretty good. Okay, so let's see what else we want to look at here. Let's look at the code for this one real quick. So let me bring up our quicksort code. Okay, so if we want to see how that's going to go, again, slightly different code. I have a little debug thing in here to show more data, not really the important thing. So what you have to do with the quicksort, the first thing you have to do is you're going to quicksort starting at 0 through the length of the array. Again, typical with recursive methods, you've got a front end that's public, and then you've got a private recursive helper. So what are you going to do? The first thing you have to do is pick a partition. Right? So we're going to pick a partition and we're going to quicksort to the left, but not quite. Right? You don't need to actually hit the middle position. So we're going to pick up a point, we're going to split it up, right? And we're going to only do those, right? We pick this position for the partition. You got to split it all up, and then you got to go to the left. That's this quicksort, and then you got to go to the right. Notice that we never actually do position, right? Position is left out because that's already sorted, as we saw. Now, to do this partitioning, right, on the way down, what do you have to do? Well, you've got to pick the pivot. We're using the index. I tried to make this really match the analogy. So you have a pivot index, I should say IDX here, and you have a wall index. You go through the items. If it's left, if it's smaller, then you increase the wall index and you do the swap. And at the end, after all that loop, you do one more swap to get the pivot item where it's supposed to be. And then you return the position of where you need to go next. And I also did have a little swap method in here, but that's not too exciting. It just has this temp variable and it just swaps the two items in the array as requested. So hopefully the sort code here makes good sense to you, right? You pick the pivot, you create two partitions, and you quick sort each of those, and eventually that all goes down and recurses through the thing and gets everything sorted exactly as it needs to be. So, and notice up here, we also make sure that we only do this work if start is less than end, not if it's equal to. So lists that are exactly one will sort of short circuit and they don't have to do anything special. So hopefully that now makes some sense. And when you see this sample code, especially if you name things right, you can sort of tie it back to the algorithm and the analogy that we talked about. All right, so one more thing that we want to do here real quick. Let me get rid of these. Okay, is take a quick peek at a sorting algorithm complexity. This is called the Big O cheat sheet. Look it up on the internet, and you can see in one-stop shopping all of the sort algorithms that we have talked about in various courses that we've studied. So you'll see the bubble sort, insertion sort. So the simple ones that we looked at before and the two new ones that we added recursively are all here, and you can compare. Notice it has the correct notation. This is big omega, big theta, big O, and it also includes the space complexity, so you can really compare them and see what the trade-offs are going to be. Again, best method if you just need one and don't have any information about the data, you're probably going to reach for a quick sort. But the nice thing is, if you know more about your data, you might be able to choose a smarter thing. For instance, if you always know that new items come in at the end, you might pick a different mechanism, right? You might find a better way. Last thing, there's some reference material. Again, I should be nice and go through and take all of these things and paste them into the comments in the videos. I'll try to get to that. It's on my to-do list. But here are some things that I found useful in referring to complexity notation. So pause if you want to take a peek at those. And then in terms of the recursive sort methods, here are some things that I found kind of useful, good demonstrations or good animations. So again, take a pause here if you want to look these up. So hopefully that all helps you understand sorting mechanisms a little better, algorithms, especially the recursive ones like the merge sort and the quick sort. And now that rounds out our understanding and terminology also about complexity. So that brings us to the end here. Thanks for watching this video series. Should be still a couple more for this course, but I appreciate you paying attention. Leave your comments or questions if you have them. Thanks.